All right. Good afternoon, class. Hopefully we had a nice long Labor Day weekend. Um, so before I begin class, I'll just sort of mention I posted a Canvas announcement yesterday on this, and for assignment 2, that last question, that weird square root one, um, the question I had originally, actually, it's going to be a little bit more challenging than I thought. It requires a different substitution method to figure that one out. So I sort of modified that last question, so it's also in the Canvas announcement. And also I'm going to, so it's also updated on that in the assignment 2 files. So just work from that updated ones. Only that last question was updated, really. Everything else is the same. So remember, the idea is you want to just solve each recurrence using one of the methods that we've done in class, whether it's the expansion, the binary, the tree version, the substitution, or the antiderivative version. So for each one, use one method to solve it, whichever method you want to use. And then, of course, for the ones that do involve using master theorem, I think there's only 2 questions on there that really involves master theorem. Also, additionally, solve that using master theorem. The rest of them, though, you just solve them using one of the methods, but the ones that can use master theorem to solve, additionally to solving it using the expansion way or the tree way, go ahead and also use the master theorem as well. So that's the update there. So homework is still due on Friday. That update shouldn't really affect getting it done by Friday because it really made that question a little easier, if anything. So shouldn't affect anything there. So anyway, let's go ahead and just begin talking about or sort of recapping from last time's lecture. So screen share 1 here. Okay, so I'm going to go and scroll to the top of this. So last time I went over sort of this example, this problem. We wanted to use divide and conquer to multiply 2 numbers. So the grade school method of multiplying 2 numbers is going to take us essentially theta n squared time to do this. So then up to this point, it was noted that the best you can do is theta of n squared to multiply 2 numbers. So lower bound mostly always tells us, well, you cannot do better than this in the worst case. So the question is, well, this was like an old sort of like thought that multiplying 2 numbers cannot be done better than n squared, which does make sense using the conventional way of multiplying 2 large numbers. So then you want to apply this divide and conquer approach. So divide and conquer basically is just like, just to recap, is divide and conquer, you break the problem into smaller pieces, and then we combine them together into one. So it's kind of like with Audi cars, they have different, plants, car plants in Europe. So one plant maybe in Austria, they work on the engine. In Hungary, they do the transmission, and maybe in Slovakia, they'll do the fuel injector, and so forth. All those parts get sent to one centralized location, maybe somewhere in Germany. They'll assemble it together at the end and get the car built. So try to take this problem, this multiplying 2 numbers together, multiplying A and B, and we want to do a divide and conquer approach. So we can actually do the following. We can break apart A and B into 2 smaller size digits, if you will. So we have A11, which is the first half of the number A. A12 will be the second half of the number A. Then B11 is that leftmost digits of B, and then B12 is that rightmost digit. So we break this number in half. And then this NO up to N over 2 is just simply adding zeros to the end of the numbers. So we're just breaking apart the number into 2 components. And this is the sound operation. This is going to be correct. All we're doing is, for example, think of the number like, let's say 1,550. We're going to have 1, 5, and then 5, 0. We break those apart, and then we multiply with the B number, break those apart, and we use distributive property to work these out, and it's going to compute this number. So if we do this, if we FOIL this out, we get this result. So basically all we have to do is break a number into 2 pieces that are both n over 2 in size, and each multiplication is a recursive function call. We're trying to basically at some point we hit our base case, let's say if A11 and B11 are both one-digit numbers, then we can multiply them in constant time and return. Otherwise, each of these, we're going to break this number apart even further and further in half. So this is going to be where we do recursive function calls. And at the end, once we have all these components computed recursively, we're going to combine them together into one answer. So this combination, we add all these components together at the very end, that will take theta of n time, because adding a bunch of n-size numbers together is a theta n operation. So all this takes theta n time, and we have to do this portion recursively. So let's go ahead and do an example. So I began this a little bit last time. So let's multiply these two numbers, a and b. So the result is going to be this big number right there. So I already calculated this earlier just to see if my work that I did does come out correctly. So a times b gives us this number. Okay, fantastic. So to do this how should I say, this in divide and conquer approach, I have a, and this is going to be my a11. That's my a12. That's b11. B12. So we simply break the number into two pieces. So using that formula from above, we get this. So if you compute each of these multiplications, then add them up at the very end, we will have our result of 36,848,980 will be the result. So basically, if the two numbers that are being multiplied are not one digit, then we have to recursively break this down. So we have to create a new function call, a recursive function call, where a will be 37 and b will be 98. So here's our new function call. So we have a smaller instance of that bigger problem. So we have a11, a12, similarly break this number in two pieces, 3 and a 7. And for b, we have b11, b12, 9 and 8, and do the same exact formula at this level. So we just, plug in those A11s and B11s and so forth to get this formula right there. And since in this case, n is 2, then it's 10 to the second power and 10 to the first for this portion. Okay, so in these cases, so for example, for all of these scenarios here, they're all going to be one-digit numbers. So we actually would call this recursively again, but it would hit the base case for all of these. So we go ahead and pass 3 and 9 into the function again. Well, so a would be 3, b would be 9. So we can't break it down any further, so we multiply 3 and 9 right away. So that'll be our base case. Let's multiply those one-digit numbers together. And it returns back 27. Same thing for 3 times 8, and 7 times 9, and 7 times 8. So it's going to just call the function again, but I don't want to go through all that, draw that whole function call, but it will call the function again. But hits the base case right away at that point and returns back those results. So we add these two together. Then we have these results here. We add those up and return that back to the previous function call, which is right here. So 3,626. We have this. We recursively computed this result. Now we have to do on this other part, because we have to recursively compute this as well, which you already did, but just scroll down and just show it. We pass in 37 in for A, 95 in for B. So again, we break this down to numbers, the two halves, if you will. So then A11 will be 3, A12 is 7, B11 is 9, B12 is 5. So we apply that same formula, same exact multiplication formula as before, to get this formula right there. And each of these multiplications are multiplying two one-digit numbers. So if you were to call a recursive function, pass in 3 and 9, it would return back 27 immediately because we hit our base case. So simply multiply those two numbers. So we don't have to recursively keep on doing work. So at that point, base case happens and we're done. So we compute this, return that back. We would compute this, return that back, and 7 times 9, we'd add these up. And then 7 times 5, we would call a recursive function call, but we hit that base case and return back 7 times 5 immediately. So now we have these components all done, and we add these all up to give us this result. So we pass that back to the previous function call. So now we have this one done recursively and this one. Now we have to work these two out. So we have to make a new function call and pass 24 in for A and 98 in for B. Let's go ahead and do that. So in this function instance, A would be, let me just make sure I get this correct. So it's 24, 98, perfect. So 24, and B would be 98. So of course, A11 would be 2, A12 would be 4, B11 would be 9, and B12 would be 8. Put my notebook here so I don't mess up this formula. So essentially, while using that same formula from before, we're going to have 10 squared multiplied by 2 times 9 plus 10 to the n over 2, or in this case 1 because n is 2 in this case, multiplied by 2 times 8 plus 4 times 9, and then plus at the end 4 times 8. So we have to make 4 function calls again for each of these multiplications, but each function call, it would hit the base case right away, so return back the immediate answer. So we would just essentially get 10 squared multiplied by 18 plus 10 to the first power, we multiply, we get 16 here, and I believe 36 over there, which will give us a total of 52 if we add these up, and then plus 32. So those will be done immediately because those are our base cases. We have size 1 numbers. So now we have these results. Well, 10 to the second power is simply we just add 2 zeros to the end of 18. So it's a linear process as well. Plus 520, add a 0 to that. Plus 32. We add these all up. 2,352. So each of these took linear time to construct because multiplying 10 to the second power is not going to be quadratic because we just simply have to add zeros to the end of 18, which is going to take 2 steps. So it's a linear process to add zeros, and adding all these up is a linear operation as well. So we get this result. So let's go ahead and sort of return that back up to this initial function call. So we have 2, 3, 5, 2. So we have that part done. Now, last part, we have to multiply this recursively. Once we have this last part done, we can combine these all together to give us our final answer. Let's go ahead and just do this. So 24 and 95 is the last function call we have to do. So we call a function again. In this function call instance, A would be 24, and B would be 95. So again, we break this apart in 2 pieces. A11 would be 2, A12 would be 4, B11 would be 9, and B12 would be 5. So that same formula applies here to this smaller instance, just like before. So we'd have, well, 10 to the power 2, because n would be 2 in this instance, because both A and B are 2-digit numbers. So you have 2 times 9 plus 10 to the first power, 2 times 5 plus 4 times 9, then plus 4 times 5 at the end. So once again, these will all yield a base case. So we would actually recursively call each function and pass in 2 and 9 for A and B, 2 and 5 for A and B, and so forth. But every time the base case would happen, so it would return those two, it would return the multiplication of those two 1-digit numbers. And then we can go ahead and use them over here. So we have 10 squared multiplied by 18 plus 10 to the first power is going to be 10 plus 36 to give us a total of 46, and then plus 20 for 4 times 5. And then 10 squared times 18, we just add 2 digits to the end, add 2 zeros, add 1 0 to 46, and then add no zeros to the 20. Add these up, this will give us a total of 2,280, and we return that back up to the initial function. So I'll write this over here, 2,280. So now we recursively computed each of these components. Now we have to work this out. So I'm going to let me see here, I'm going to go back to my notes. Stupid, I don't know why it keeps popping up. Okay, so let's go back to my notes for a second. So essentially at this point, I'll use green to do this. This will give us, if I go ahead and take this 3,626, add 4 zeros to this, plus this summation right there, which will give us 5,867. We just add 2 zeros to that, and then plus, well, I guess just this result over there. If you add all these up, we actually will get this result right here, which I've already pre-done this, so this is going to definitely work. So we got the same answer using this approach. So I guess the question here is, okay, so we found a different way of multiplying two n-digit numbers. All right, so let's go ahead and try to look at some analysis and see what's the runtime of doing this. So we know the grade school method is going to give us theta n squared runtime, where n is number of digits in a number. So let's go ahead and look at the see if I, okay, over here. So this is going to be the case. So each multiplication is going to result in a function call. And each time we're passing in a number half the size, a half number of digits than before. So basically every recursive function call, we're passing in n over 2 size numbers into each function call. And we're doing 4 of these. So 4 multiplications of n over 2 size numbers. And then adding all the components together at the very end takes n time because we're doing a bunch of additions. Even doing this, multiplying by 10 to the power n, we're going to add n number of zeros to the end. So that's also a linear process as well. So this addition right there will take a total of n time to add all these up. So let's look at the recurrence relation for this. So let me just go ahead and look at time complexity. So let's go ahead and sort of paraphrase this. So each multiplication calls a recursive, or makes a function call. So it's going to create a function call. Sort of with n over 2 sized numbers. So basically, we're going to pass in two numbers that are n over 2 in size, so half number of digits than we had originally. And it's going to be 4 multiplications in total. And then it takes theta of n time, so it's going to takes theta of n time to combine the partial results together. So let's go ahead. Now we have this information here. Let's go ahead and just, how shall we say, create the recurrence relation for this. So we're going to have T of n is going to equal 4 T of n over 2 plus theta of n. That's the recurrence because each function call, we're passing in two numbers that are both size n over 2. So we cut the input size in half each time. So we're passing a11 and b11 into a new function call instance, which is a11 is half the size of the original number a. And we do this 4 times. We have 4 multiplications, 4 recursive calls. And then plus theta of n to combine them together. And of course, our base case, T of 1 would just be 1. It's constant time to multiply two numbers that are both size 1. So we can go ahead and just sort of use the master theorem on this. I believe this will give us case 1. So this will have, so T of n is actually theta of n squared. I believe it's case 1 of the master theorem applies to this. So you can also verify this in fact will be definitely theta of n squared. So, okay. I mean, that's fantastic. So we found a cool, neat, overcomplicated way to do the same exact thing we were able to do already because we multiply these numbers together and it took theta n squared time to do, which is the same runtime as we had before. So, okay, why did I spend, 20 minutes today and maybe like, I don't know how much time last time covering this? Well, the deal is that first step is you first want to find a way how to separate this into components in different individual pieces by calling recursive functions to compute each result and then put them together. And by doing that, the beauty is, well, what if we could find a way to actually, have less multiplications? So, all right, well, let's go ahead and copy the formula from above. I'm going to copy this down and sort of reuse that over here. So here's the original formula. Let's go ahead and just copy this. So what I'm going to do is what if we can actually do this in, maybe we can reduce one of these operations. Let's scroll down here. And see if I can paste this here. Perfect. Okay, so I forgot the name of the person who had this algorithm, but let's go ahead and just try an alternative approach. So over here we have a11 times b11. We can't really improve any of these multiplications. You're going to do it recursively and do exactly the same thing. But what we're trying to do is what if we can actually maybe do one less multiplication, actually. So right now, a11 times b11, that's kind of, well, we can't really do anything there. a12 times b12, well, we can't do anything there. But this is an interesting part. We actually could rewrite this a little differently, actually. So let's go ahead and do that. So this alternative approach, which I'll just label this as alternative approach. Is it 1p or 2p's in that word? Well, anyway, not important. I'm really having issues spelling stuff these days. So anyway, this result right there, we can do is rewrite this in the following way. So we could do this. A11 plus A12, multiply it by B11 plus B12 minus A11 times B11 minus A12 times B12. So let's try to replace that whole entire part with this. We're going to replace it with that. Now, you're looking at this saying like, well, how is this actually better? Because we actually have 3 multiplications here. This only has 2. Well, the issue here is that we already computed this earlier. We can simply reuse this right over here. So we can take that result that we computed recursively and simply store this into a variable, local variable. And same idea with this number. We can take this result and simply store this into a local variable. Now, the order in which we compute these don't matter because just like with the car assembly thing, let's say in Germany we're going to assemble the Audi together. It doesn't matter if first the transmission gets there and then the engine, or the engine then transmission. It doesn't matter. As long as they both get there, we can assemble them together. So same idea here. Divide and conquer is amazing how we can sort of do this completely independently of each other. Doesn't matter which one gets done first. As long as we get these 3 components, we're good. So if A11, we can first compute A11 times B11 first, then compute A12 times B12 next, and then we can do this work by adding n digits to the end of this. And we can simply reuse these and do this, take this whole entire part here and replace this inner part. So then really, right now, we only have to do only one multiplication because these two we've already done before. We simply reuse those. So we have to do only one multiplication. Now, we do an extra addition over here, a11 plus a12, b11 plus b12, but it's okay. It involves doing an extra addition. So you have to do two additions and two subtractions, but it's okay. We do a couple of extra theta n work. So doing a few extra additions is not going to hurt the runtime. So for example, in the above example, we had to do maybe, one addition, so 1 plus 2 plus 3. Now we're going to do extra couple of additions, but doing a few extra additions, though, is not going to hurt the runtime. It still will remain theta n to combine all these together. So then the question is, will this even in fact work? Well, let's go ahead and just FOIL this out and see what happens. So just go to my notes. Actually, I can do this kind of without that. So it's a11 times b11, if you FOIL this out, plus a11 times b12, plus a12 times b11, plus plus a12 times b12, and of course subtract it with a11 times b11 minus a12 times b12. So you notice over here, well, these cancel out. And also you can notice over here that b12, so these also cancel out. So we're last left with this. That's the only thing left over. And this, I believe, matches right there. A11, B12, A12, B11. It matches. So this work right here, if we replace that, I'm going to maybe box this in completely. If we replace all of that, all of this, with that inner function, with this inner portion there, it's going to give us the same result, but we had to do only one recursive call. Now there's more additions to be done here, that's correct, but doing a few extra additions, though, is not going to hurt that runtime of that combining. We do a couple of extra theta n processes. We do maybe 3 or 4 extra theta n work, which is going to be overall still theta n time to actually combine this. But now we only have to do one multiplication instead of 2 inside of this portion right there. So now we have a total of 3 multiplications. You have one right there, one right here, and one right there. So now we can do a new recurrence relation. We have t of n equals 3 times t n over 2 plus, still going to be theta of n. Maybe a few extra theta of n steps, but overall, it's still going to be theta n time completely to sort of combine these all together. Then t of 1 still remains 1. And then now, if we solve this recurrence using the master theorem, well, it's going to be theta of n up to the log 2 of 3, if I can just make sure, yes. It's going to be, again, case 1, which if we were to sort of get numerical result, it would be theta of n up to the 1.585, which is better than theta of n squared. Actually, pretty much better. Actually, in this case, asymptotically better. But it's going to make a pretty big factor. This is almost actually, this is very similar to n root n, which is much better than n squared. So, because we took this problem and we divided it up into small components, we were able to find some trick to find a way to rewrite one of the components, like over here, to reduce the number of function calls. So only reducing by one function call actually made this runtime asymptotically better. But it required us to do a few more extra additions, but that's okay because it's not going to make a big problem. We do a little extra work in that conquer part of divide and conquer, that's fine, but by doing that, though, we do one less multiplication, which gives us a better runtime. So basically, this method is really better to use if, let's say, we have a very big value for n. So let's say we have, so the example I gave you in class, we just did 4-digit numbers, then really the grade school method is probably a better idea. This is mostly applied for if you have 2 very big numbers, like let's say 100-digit numbers or so, then this method is going to give us a better runtime. So as always, remember, in algorithms, n has to be a very big number, typically, to really see any differences. So for example, like on bubble sort and merge sort, if the size of the list is 20, then you don't see a difference. But for 1 million, now we see a difference with bubble sort being much slower than merge sort. So same idea here. So n has to be large to see this result. So then another question is you're wondering, well, when would we actually have to do this? Or why would we actually ever want to do this method? And I guess sort of the answer to that question is, well, why wouldn't you want to do this? I mean, okay, we have two numbers that are both n digits, they're big numbers. And okay, I have a slow way, n squared time to do this, or I can do this in n up to the 1.5 runtime. So why do it slower? This algorithm is actually not that hard to even code really, and we can do this in much faster time. So yeah, of course, if you can do it faster, why do it slower, I guess, is the right idea. That's really kind of that's kind of common sense. So the answer is, why wouldn't you? But of course, for small size input, then yeah, I wouldn't. But for big input, this is a much better approach. Now, I'm not going to do the example of this approach. This will be kind of for homework exercise, but really it's not going to be too much more difficult than what I went over in class right there. So I'm going to try to make the numbers relatively small so it won't take you hours to trace this out on paper, but you're going to have to implement this algorithm for homework assignments. I went over the more straightforward approach just to kind of, give us an idea of how this works. And this method is the same idea, except you're going to have to do more. You have to first compute these two results recursively, or compute this result recursively, get that number, subtract it from A1 and B1, that'll give you that inner term. So really it's the same idea. So I'll have you for homework assignment, work out an example using this enhanced version of divide and conquer. So we kind of see one example of where divide and conquer does, we saw several. So for 302, we had merge sort and quick sort and all that, you saw better results than using a straight, normal, non-divide and conquer approach. But here's another example of where divide and conquer does actually give us a good result. So I guess I'll post these notes up onto Canvas, and you can revert back to these notes when doing the homework assignment, which will involve doing this multiplication of big numbers. So now let's go ahead and talk about a different divide and conquer problem. So let me go ahead and just, I'm going to just go over here and add a page there and just go over matrix multiplication. So once again, we're going to go ahead and take this problem, multiplying matrices, and try to apply divide and conquer to work these out. So let's go ahead and just set this problem up. So we're going to multiply two square matrices, which really means that they're going to be both n by n matrices is what this really means. So both will be n by n. And we're going to assume, just to make things easier, assume that n is a power of 2. Just to make this problem simple to break apart. So just like for the multiplying two big numbers, we're going to have the examples for homework also be where there'll be powers of 2, just to make that process much more simpler to do. So okay, so the straight normal way of doing this, let's go look at our old sort of type of code here. So let's go ahead and sort of assume. So let's look at the pseudo code to multiply matrices A and B. So we're going to let C be a new sort of a new n by n matrix. So that's pretty standard, nothing too complicated there. Then of course we'll have our sort of loop. So for I equals 1 to n, this is, I guess, maybe a little bit of Python type code, I guess, if you will, except it would be for I in range 1 to n, but it doesn't really matter. Then we'll have another loop here for j equals 1 to n. Then we're going to set Cij equals to 0. And then, of course, we're going to have another loop right there. So for k equals 1 to n, we're just going to have Cij equals Cij plus Aik multiplied by Bkj. So that's like the standard sort of way of multiplying two matrices. So remember how this works. I'll just quickly draw this here. We have two matrices. I believe the ways we just sort of multiply this with all of these in that type of fashion. So then this multiplies to this inner. So it's that matrix multiplication sort of operation, basically. So nothing fancy there. So the runtime for this is pretty simple. We can go back to our 302 notes and work this out. We have a nested loop of size 3. Each runs in n time. So obviously this is going to have a theta n cubed runtime. No surprise there. So once again, we're going to try to see if we can improve this from n cubed to a smaller amount. So once again, we're going to go back to our old friend divide and conquer to solve this problem, or try to solve this problem faster. So let's try, this is like the regular straightforward way of doing this. Let's try the divide and conquer approach to this problem. The third loop is inside the second one. So these two statements is like the Python way of doing this, I guess, if you will. These two are inside of this second loop. So it's a nested loop of 3 levels, so n cubed. So they're all in the same scope then. All right. So so now what's going to happen is, well, let's try to use our divide and conquer approach to solve this and see if we can get a better result. So let's look at our divide and conquer approach. So we're going to have two matrices, A and B and C. So A times B, and we're going to store that into matrix C. So let's go ahead and first set this up. So A will equal this matrix over here. Then B is going to equal another matrix, the same size. I'm going to fill this in a second. And then C will be the resulting matrix right out here. So we're going to break the matrices A and B into 4 quadrants. So we're going to have A11, A12, A21, and A22. So these are not going to actually be elements, or they could be, but these will be just quadrants. So we're going to break this into 4 quadrants. So these could be submatrices. Now, if let's say if A is a 2x2 matrix, then A11 would be a single element, so would A12 and so forth. So that's going to be the base case. Once we have A11 is size 1, we hit our base case. But first, let's go ahead and just divide these up into quadrants. Like that. And of course, C11 also can be broken up into quadrants as well. C21, sorry. And C22. And of course, I'll have this also in quadrants. So we can simply break each matrix into quadrants very easily. We just have to divide the sort of the rows and columns by 2. So basically each of these will be n over 2 by n over 2 in size, each of these. So anyway, we'll go over that analysis in a second, but let's first go ahead. So we're multiplying A times B to get C. So just sort of put this over here. At the very end, we're trying to take C is going to equal A times B. So the result of this, using divide and conquer, so yeah, I'll write this out and then I'll zoom out after I write this little part here. So C11 will equal A11 times B11 plus A12 times B21. And then C12 will equal A11 times B12. It's using a standard method, so we're just taking A11 times B11 plus A12 times B21. So it's basically we're just doing this. That's what's going on. That's going to give us C11. So no real magic here. We're just doing this kind of in parts like this. Then C12 is A11 times B12 plus A12 multiplied by B22. Then C21 is equal A21 times B11 plus A22 times B21. Then I'll scroll down and I'll zoom out once I get the whole thing written so you can see it all. So A21 multiplied by B12 plus A22 multiplied by B22. Then I'll zoom out so you can see all of this. Hopefully it's still visible on the stream. If not, let me know. I can zoom in a bit. But I can sort of scroll. Let's see if I can try to fix this. So why isn't this doing it? Control Shift is supposed to let me. Whatever. Anyway, there's going to be our result. So we split into these 4 quadrants, and we just compute these C quadrants by using this formula right below. So once again, what we're going to do is we're going to have to pretty much just divide this up. So A11 and B11, each of these components, so each A11, B11 is going to be just n by 2. So it's going to, I'll put this over here. So I'll put this here. So each quadrant will be a n over 2 by n over 2 sized matrix. I think I'll just also box this in as well. So in a sense, we're sort of dividing the problem in half again, because we're taking the matrix and dividing in half the number of rows and columns and creating 4 of these sort of n over 2 by n over 2 size matrices. And each multiplication, well, as you guessed it, we're going to have to recursively do the exact same thing on the smaller size. So A11 times B11 will create a separate recursive function call where A11 will be the A for this subproblem, and B11 will be just that O and B value. So we do that recursively. And same thing we do recursively for A12 times B21. So you have to create, looks like 8 recursive function calls. And each function call is going to be n over 2 by n over 2 size matrices. Then we have to add these all up. So we go ahead and put some more notes over here so we can get a better idea. So I'll zoom in on this. We have to kind of modify this a little bit as well. That's going to be later on. So basically, again, each multiplication is done recursively by passing in 2 matrices of size n over 2 by n over 2. And after we compute all of these parts recursively, then we have to, again, just like our typical divide and conquer type approach, we have to add these all up together. So then we combine all of the subproblems, or submatrices, if you will, which will be subproblems, I guess, over here, by sort of adding 2 n squared over 4 sized matrices. And then we want to put each one into that C and assign each submatrix into the correct quadrant of C. So we're adding several n squared over 4 size matrices. So this addition, this combining, will take in fact theta of n squared. So this part takes theta n squared. So basically, that combining part, or that conquer part of divide and conquer, for this instance, it takes theta n squared time, because we have these n by n over 2 by n over 2 size matrices, and adding these two matrices, so one that has n squared over 4 in size plus n squared over 4 in size matrix together takes n squared time to add. So each of these parts, let me just scroll up here for a second, each of these take theta n squared time to add. So we do at most 4 additions. So the overall runtime to combine these together takes theta n squared time. So we'll use that later on when we do analysis. Let's first do an example of this, of course. As always, you have to do an example. And then we're going to show the analysis for it then. So of course, each one is done recursively. But at the very end, our base case will be, so the base case for this problem is when we are multiplying two matrices that are 1 by 1, if you will. 1 by 1 in size. That can be done in constant time. So when we hit that 1 by 1, multiply those two, return that back up. Done. Otherwise, you have to break it apart into these these 4 quadrants. You're going to have 8 multiplications in total. Get their submatrices back, add them together, and assign them into the correct quadrant of C, which we know what the quadrants are because this formula basically tells exactly which quadrant these have to go into. So once again, that's going to be our process. So maybe you already can kind of see the runtime for this, but let's go ahead and do an example, and then we'll go ahead and do sort of analysis of this. So I have a worked out example already done, just so I don't, have to do this in my head right here in front of class and make a mistake. So let's go ahead and do a new example, because we're going to have to, for a homework assignment, have to do something along these lines, or maybe a different version of this, but it's going to be very much based on this example. So we're going to have A and B. So I'm going to just do an example matrix here. So you have A, which will be 6, 12, 8, 4, and I'll close this up. And we have 7, 10, 3, 2, 9, 4, 5, 1, 12, 13, 14, and 15. Like, I probably can't fit B over here on this. Maybe we can try to fit B over here as well in the same frame. I probably can somehow squeeze this in. I think it'll work. So we'll have 12, 11, 5, 6, 2, 4, 8, 10, 1, 3, 7, 9, and then of course last row 8, 4, 2, 1. So in this case, we have these two 4 by 4 matrices. So we'll stick to using powers of 2 for the sizes just to make this process easy. So of course, we're going to have to break this into 4 quadrants for each one of these. So just essentially just do that. So basically, we're going to have this be our A11. This will be A12. This will be A21. This will be A22. Then we'll have B11, B12, B21, and B22. And then we're going to have to create our C matrix over here to be our resulting matrix, which we're going to kind of iteratively, step by step, create this. Let's scroll down a little bit more. So we're going to also have this in quadrants as well, just so we can visualize all this. So this will be our C11, C12, C21, and C22. So we have our everything set up for this problem. Now we have to go ahead and, of course, work these problems out. So let's go ahead and first compute C11. Let's start with the top left first. So C11, just to recap, let's copy our notes. A11 times B11 plus A12 times B21. So we're going to have to first compute this. So A11 is going to essentially be this. It's going to be 6. So we have to first do this recursive call. So right now we're going to first process this A11, B11 recursively. So A11 is going to be this matrix over here. So A11 is going to be this. 6, 12, 7, and 10. And in our B11 in this case, well, it's going to be essentially 12, 11, 2, and 4. And we have to compute the C for this, which I'll put that later on. So right now, again, we have to break this into 4 quadrants also. But we see here that now we're going to have these size 1 matrices in this situation. So of course, we have to do the same exact process, have to compute A11 times B11, then plus A12 times B21, but those can be done in constant time. So I'm going to go ahead and kind of shortcut this, but in theory, we have to call a recursive function to do all this, all these, these base cases, but I'm going to just kind of shorten this a little bit. So we're going to first compute the A11, B11 component of this. So you first have to do the first step. So I'm just going to shortcut this to like not have to do too much steps. This will give us a total of 96, 114, 104, and 117. We did this by basically just taking this A1, this matrix, and this matrix, and doing that same work. We computed sort of, so in this smaller instance, this will be your A11, your A12, A21, A22. This will be your B11, B12, B21, B22. And then this is going to be your C11, C12, and so forth. I'll do the rest of them as well. So I kind of did this in one step just to avoid having to have to take forever. I mean, it's already taking a long time doing this example, but it would take a lot longer to do all that. But we do essentially, let me go back here for a second, my notes. We're doing all of this on that smaller instance. So we computed C11, C12, C21, C22, and all of these were done in constant time because each of these A11s, B11s, and so forth, all of them were 1-by-1 matrices. So we did this all in constant time, and we computed the C matrix for this smaller instance. So that means this is going to be A11 times B11 is going to be this result right here. So now we have to compute A12 times B21. We have to compute this separately in a different function instance. So let's go ahead and do that one. So I'll put this actually below because I don't have room to write from left to right over here. So in this new instance, a new function call is going to be done. In this function call, we're going to pass in A12 and B21, which will essentially be these two smaller submatrices, 8, 4, 3, 2. This will be, let me just make sure I'm consistent with my notes. Yeah, so this will be your A for this new function call instance. This will be your B, which will be essentially 1, 3, 8, 4. And of course, we can break this down into 4 quadrants as well. And we're going to do 8 function calls, but each of them will be done in constant time because each of these submatrices are all size 1 by 1, so it will not have to keep on recursively breaking it down. So to make things simpler, I just kind of did this in kind of one step, essentially. We have to do those 8 sort of multiplications and add in those 4 additions to combine to create this matrix. So this matrix, we have to also, this will be our C matrix for this smaller instance. And this one's going to essentially be 40, 40, 19, and 17. If you apply that same formula on this small instance, this is your A11, so I'll put this over here just to make it so it's A11, A2, A12, A21, A22, B11, B12, B21, and B22. So we have these 8 components here, and we apply that same formula on this smaller instance. And each one, because A11 times B11 can be done in one step. You don't have to recursively break that down any further, but you would call a function and pass those into that new function. But in that function body, the base case gets sort of activated and it returns 8 back up. And then we just go ahead and then multiply 4 times 8, because A12 times B21 gives us 32, add those up, and that 40 gets stored into C11. So we'd have to do that. But we can, so for the homework assignment, you can actually, if you get to this point, you can just kind of autonomically just do this. You don't have to actually do more recursive calls because it will take a lot of steps to do all that. But anyway, this matrix is the result of A12 times B21. So we simply have to take this matrix in red, add it with this one in red. So actually, I'll put this here as well. So this is C11, C12, C21, C22. So we're going to return these two matrices back up. So this will be the result of A11 times B11. That's the result of A12 times B21. We add these two red matrices together to give us the final result, which I'll just do this kind of quickly here. This is going to give us the result of 136, 154, 123, and 134. So that's the result of adding those two red matrices together. So that gets returned all the way back to the very beginning. So this matrix will get returned all the way back up here. So we have our first quadrant done so far. 1, 3, 6, 1, 5, 4, 1, 2, 3, and 1, 3, 4. So we first computed C11. The C11 is going to be the result. C11 is going to be essentially this green matrix. We had to take these two red ones, add them together, and return that back up, and we store this into C11. Fantastic. So the first part is done. Well, now we have to go ahead and compute C12 next. So let's go ahead and do that. So C12, I'll put this over here. C12 equals, let me just make sure my notes are all correct here. So you have C12 will be A11 multiplied by B12 plus A12 multiplied by B22. So we already know what A11 and all those are. We already broke those matrices into these 4 quadrants. So we can go ahead and use these right here. So A11 is going to essentially be the following. So A11 is this matrix. 6, 12, 7, and 10. And then B12 is going to be this matrix. 5, 6, 8, and 10. So we're going to pass this matrix this matrix right here, this is going to be our A, that's going to be our B for a smaller instance. We call this function recursively and pass these two matrices in. So we're doing the same process, but on a smaller size matrix. So in this case, this will be your A11. Actually, I'll do this, I'll bring this into quadrants again. A11, A12, A21, A22, A11, A12, oh sorry, it's B11, my mistake, B11, B12, B21, and B22. So we have to apply that big formula to compute, because we're going to have this C matrix we're going to create over here. So I'll put this over here for right now. This is also going to be broken up into 4 quadrants as well. It's going to be the resulting C matrix for this smaller instance of the problem. So remember, we have to do A11 times B11 plus A12 times B21 to compute C11, and so forth. So you have to apply those 4 formulas because you have to compute the C11, C12, C21, and C22 for this smaller instance. So I'll just kind of do this really fast. So in this case over here, we'd end up getting 126 for C11, 156, 115, and 142. This will be essentially a C11, C12, C21, and C22. So you can try it. If you apply that same formula on this smaller instance, you get this result. So this is going to be that first matrix you had to compute. Because remember, for this instance of the problem, to get C12, we first had to compute this matrix, which is right there. And now we have to compute this matrix next. So we're going to pass an A12 and B22 into another function call. So it's going to pass into smaller matrices than before, but we had to create another instance of a function. Again, this will be your A matrix. This entire submatrix will be the B matrix for this subproblem. So let's go ahead and do that one next. So then A12 is going to be the following matrix for the second part, for part 2 of this problem. You have 8, 4, 3, 2. So going from our original matrix, A12 is this submatrix. And then B22 is going to be this submatrix. 7, 9, 2, and 5. And of course, we break this down into its own quadrants. And then this is going to be your A11 for this matrix. A12, A21, A22, this will be your B11, B12, B21, and of course you have our B22 right there. And of course we're going to have to compute C11 for this instance. So C11, remember it's A11 times B11 plus A12 times B21, which these can all be done in constant time because A11 and B11 are size 1 matrices. And of course, C12 would be, of course, A11 times B12 multiplied by A12 multiplied by B22. So same process, except now the beauty is that they're size 1 matrices, so we don't have to keep on recursively breaking it down. It'll return back the results immediately because they're size 1, or base case. So let's go ahead and just sort of, shortcut this and compute our C matrix over here for this smaller instance of the problem, which actually would be 64, 76, 25, and 29. This will be a resulting C matrix. C11, C12, C21, and C22. So this red matrix, we're going to box it in red now. This is going to be the result of multiplying A12 by B22. So we have this matrix and this matrix. Those are going to be this result and this result. We have to sort of add these up to get C12. So I'm going to have to add the red matrices up. And the result is going to be so 190, 232, 140, and 171. And I'll put this here in green. It's going to be the result. It's going to be essentially, this is going to be the C12. Return this back up, way back to the very top over here. C12 will be assigned that green matrix, which means C12, which is this, we're going to assign that quadrant right over here. So we're gonna put 190, 232, 140, and 171. So we finally computed C12 at this state. So let me see here. I think I'll keep talking about this, but I mean, trying to think if I should continue with this. Maybe I can sort of finish this up next time. But anyway, let's go ahead and I'll just set up the next part, and then we'll go ahead and we'll probably stop. I'll say a few things, and we'll stop here. So now we have to compute C21 next. So let's go ahead and write the formula here for that. So I want to next compute C21, which would just be essentially A21 multiplied by B11 according to our formula that we have, and plus A22 multiplied by B21. So once again, A21, B11 are defined. Those are the quadrants that we've set up on the original problem. And same thing for A22, B21. We simply just have to go ahead and do the same process. And all we do is A21 is going to be a parameter passed into a function call. So for that function call, that A matrix will be essentially just A21, but it's a separate instance of the function. So remember, we call a function recursively. We keep on passing in smaller matrices in until eventually we pass in size 1 matrices. And at that point, we can go ahead and return those. We can multiply those in constant time because multiplying two sort of 1 by 1 matrices can be done very quickly. So we have to do the same exact work on this part. So I'm going to go ahead and continue on this. So C21 and C22 parts. Next time, we'll go ahead and compute these and sort of fill up our C matrix up. And that result is going to be the same result as if you would have done the regular, ordinary way for multiplying two matrices together. And then, we'll analyze the runtime for this algorithm as well. And then we're going to go ahead and see, well, what's the runtime of this? Is it better than our original method? And if it's not better, well, can we again improve? And since we, use divide and conquer to split the problem into smaller pieces, because of that, we could try to maybe eliminate, a recursive function call to again try to enhance runtime. So that'll be it for, I guess, for today. I will finish this example up next time and then go over, more content on this. So for right now, I guess, take care, stay safe. Thanks for watching, and I will see you guys on Thursday.